Noticed a few people asking for a vid modding guide for the GTX 260 competition. So this is going to be a hopefully beginner to electronics friendly and not overly incoherent explanation / ramble about vid modding. So we'll start off with what is vid. Now vid is basically just a way of telling certain voltage controllers what voltage to output. So in a lot of cases, if you want your voltage controller to be able to do multiple different voltage outputs, let's say for power saving, or you're making a motherboard where you want voltage control and the potential to put many different CPUs in the one socket that might run at all different voltages, you need a way to be able to change the voltage while the processor is running and just in general without having to go to a really complicated thing with lots of voltage dividers. Voltage dividers are great for simplicity, but they're really bad for being able to dynamically change the voltage while it's running, or just to change it in general, because you suddenly need to be able to basically change your voltage divider, which messes with the compensation loop, and it gets very complicated very quickly. So what we're going to look at today is the vid code for Intel VR 11.1. Now there's many different vids out there. There's like VR10, which is the previous spec to VR 11.1. Certain controllers basically have their own proprietary ones. It really doesn't matter too much. Right now, we're just going to focus on this one example because that's what basically every GTX 260 and Fermi card uses that has vid controllers that use vid. Or even later ones, like all the way up into like GTX 770, 780s, you get controllers that just use vid, and it's pretty much always VR 11.1. So the way Intel VR 11.1 works is it's an 8-bit vid code. Basically, each vid has a certain millivolt value associated with it. So here, for instance, vid 0 is 6.25 millivolts, 12.5 millivolts for vid 1. Now you'll notice that every time it's doubling, which is really nice to work with. It makes the math even easier. But the basic way this works is you start with 1612.5 millivolts, and you subtract away these if there's a 1 there. That's the easiest way to do the math if you don't understand binary well. You basically treat this as, if there's a 1, yes, subtract that amount away from this. Makes the math nice and easy. That way, you can see that for 1.6 volts, we start with our magic number here, then we subtract away 12.5 millivolts because there's a 1. And there you go, you get 1.6 volts. Now, in special cases, there's also these off ones up here. That means anything above 1.6 is treated as just VRM off. Don't put out any voltage. The same is true for our bottom vids. Notice all ones and all ones but 1 0. Then that on 0 is in the 6.25 millivolt column. That's off. Same thing here. All zeros off. All zeros in the last one being a 1 off. Anything under 0.5 volts is considered kind of invalid. It might just result in VRM off. I don't exactly know. It'd be up to the controller. The ADP 4100 actually goes down to 0.375 volts. That exact detail really doesn't matter. Again, you are not going to run anything under 0.8 volts in practice, basically. Even for power saving, it's just not really happens, so don't worry about that one too much. You can also see, again, what makes this really easy is if you want to, in your head, calculate, I need to drop the voltage by, like, let's say you're at 1.55 volts and we want to go to 1.5 volts. Well, you can immediately know that, again, we start from our main thing, we subtract 12.5. This is pretty easy if you want to get to like the big round numbers. It's just always keep vid1 on. It basically gets you down to these. And then the other ones are really easy to work with. So I want 25 millivolts more or less, change vid2. 50 millivolts more or less, change vid3. Vid4 for 100, right? So 1.5 volts, subtract the 12.5, and subtract another 100 from here, right? You start with here, start with 1.6, subtract that, then you subtract another 100, 1.5 volts. For 1.2 volts, the same thing. We start with the 1.6125, remove the 12.5, and then we remove another 400 millivolts, so we get to 1.2 volts. Okay, so now we can get to some practical examples about changing vid codes and what vid codes actually look like in practice. So here's for an example, I started with the vid for 1.175 volts. And if I want to increase the voltage by, let's say, 200 millivolts, what I basically want to do is switch it over such that vid 6 is off and vid 5 is on, right? There's a 200 millivolt difference there. Perfect. Now, the important thing that you'll notice is that when I did the transition, if I turned this one off and then this one on, I went up in the meantime to 1.575 volts. You might want to avoid that. Now, if it's at idle, it's probably fine in practice. The current will be low enough, and these voltages aren't that high that you really have to worry about oxide breakdown. But you have to sometimes keep in mind when you're doing transitions like this about the order that you flip the switches in order to, avoid your intermediate values from being really high. Now, the way that your CPU gets around this is by there being a tiny amount of delay, and we'll get into that later. And that tiny amount of delay is between when it detects a change in vid and actually changes the output of the VRM. Because your CPU within like 400 nanoseconds can easily change all the vid codes and doesn't have to worry. You're not going to be able to do that, though. You're going to have to deal with, okay, what are the intermediate values? How do I do this properly? But this is actually pretty easy to deal with once you get the hang of it. You just work around it a bit. And honestly, aside from accidentally crashing or, maybe let's say accidentally turning your VRM off, the actual damage to silicon perspective is pretty minimal as long as you keep an eye on what the output voltage is. Usually the assumption is you're not going to run it at 1.5 volts by accident, without paying attention. At the same point, feedback mods are also, this is a lot safer than a feedback mod in the sense that you can't accidentally set way too high. So for instance, if you don't put a limiting resistor on your feedback mod on some controllers, you can easily have it go to 3 volts by accident, especially if you turn your pop the wrong way and you started up the card with it set to max voltage. Maybe you sent 12 volts through your processor right away. Whereas vid, you really can't do that. The most you can get it to output is 1.6 volts. So you don't have to worry unless you put a feedback mod with it. And then you accidentally output the 1.6 volts that would then be multiplied up by 20%. And then, but that's just getting into a lot more complexity. We won't worry about that right now. And the other thing to note here is that when you're calculating VIG codes is that it's often just really nice to plan it out ahead of time and keep track of which switch is according to which vid bit. So one of the easiest mistakes to make is to think, oh, I want to get the vid for 1.4 volts, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0. But if I put that on the switches on the opposite way, right, we've moved these over 1, you'll get 1.18 volts instead, and you'll be very confused. So just keep in mind that when we talk about these vid codes, the order of the bits can be flipped in practice on your switches or on the controller versus the order that we're looking at them here. Okay, so now we're going to get into the whole how this is actually implemented on the controller and how the electrical part of it looks like. So on the ADP 4100, which is the main controller that we basically have to worry about with GTX 260s that really need vid mods, you notice at the top here we have vid 0 through 7. Now you'll also notice, like I just mentioned, this is actually reversed the order. Notice 7 is on the right, whereas 0 was on the right earlier. So when you do the vid codes with these, you just have to really keep in mind the order. Also, I highlighted VCC3 here. That is a very convenient voltage to use to help control the voltages for these. So don't worry about that too much right now. The main thing to keep in mind is that the way these vid pins work is that on each one, all we care about is whether there's a voltage that is a logic high or a logic low. Now, high means a 1, low means a 0. Low, as they basically spec here, is anything under 0.3 volts, and a logic high is interpreted as anything above 0.8 volts. This means that the controller really doesn't care if you put 2 volts or 3.3 volts on that pin as a logic high. It interprets it the exact same way. These are digital signals, so it's either on or off. It's not an analog signal somewhere in between. So the important thing basically here is that we have to basically control these either the GPU will control it or we're going to override it and disconnect the GPU such that there is either a logic high or a logic low on each pin, and that will form the output voltage of the vid. This is really easy to do because we don't have to feed a serial signal in or something that changes. We don't have to set it at an exact certain point. It's just static, constant thing that we just change from one static state to another, essentially. Now, the important part of this on the ADP 4100 and why this is really important is that the ADP 4100 actually under undervoltage and overvoltage thresholds relative to the DAC output. Now, the DAC is this digital to analog converter, just down in there. And basically what that does, it takes our vid pins in and produces, along with this precision reference, a reference voltage that the feedback is, basically what it does is it will change the output voltage such that the feedback voltage will equal the DAC voltage. So in a lot of controllers where you see a voltage divider, it will have a single static reference voltage of like 0.8 volts that you're dividing. Your divider will basically create a steady state where when your output voltage is what you want, the feedback voltage will be 0.8 volts. And the controller will basically do everything it can to maintain that circumstance. And we're basically doing a similar thing here, where feedback is being maintained at this DAC voltage. But because we can change this DAC voltage with the vid, that's how our output voltage changes. And because we are simply moving the DAC output, we don't have to worry about our undervoltage or overvoltage threshold because it's set relative to that. So in this case, somewhere between 200 and 400 millivolts over, or 400 millivolts and 600 millivolts under that DAC voltage. So this completely gets rid of our overvoltage protection issues that you might run into with a feedback mod. And you can still use a feedback mod to get maybe 100 extra millivolts and mess with that range, but more than that is where you really start getting into problems. And that's why vid modding is so important on these. Now, what's nice about this is the controller also explicitly supports dynamic vid changes while it's running. Now, they actually spec this very carefully here with basically from a vid code change to the actual feedback voltage change is 200 nanoseconds. It'll wait that long. And if you put a vid that's an off vid, so one of those ones that's like above the 1.6 or basically below 0.5, it'll wait 5 microseconds before trying to turn off. So just to check, do you really need this? Now, as you can tell in both of those cases, this is an implementation detail for a processor or like a microprocessor changing the vid. You are not going to move it that quickly with your hands flipping switches. Just unrealistic. This is how it avoids the in-between states if the CPU is changing it, for instance. Now, here's a simplified schematic view of an ADP 4100 with its vid outputs. These pin notes should be correct. I didn't really double check them, but this is just an example. This is not the exact way the GTX 260s are implemented on this. Do not look at it that way. This is a simplified example. So in this case, we have a bunch of resistors that connect certain vid pins up to 3.3 volts. Now these are pull-up resistors because they take the voltage and they will help pull it up to this higher voltage. So basically each pin on the ADP 4100, they mentioned this somewhere up above, but basically each pin on here has a pull down, which is basically an internal resistor that connects each of these pins to ground. That means that if you left it floating with no connection, it will be held down to 0 volts because there's a high impedance resistor to ground. Now, because you're even if it's like 100K to ground, if your effective resistance to any voltage is like a couple giga ohms, obviously it's going to be right near 0. If you do the voltage divider math, it will tell you that. Same thing here. If you have a 10K resistor connecting to 3.3 volts and 100K to ground internally, basically it's going to be at above, like well above 2 volts. It's going to be well above our threshold. We don't have to worry, and that way it'll be interpreted as a logic high. Now this is important because our GPIO can't, our GPU, which will have its certain pins on it called GPIO pins, which will then raise or lower the voltage on that pin, can't tell the controller what voltage to output until it initializes, until it turns on, right? And to do that, it needs some amount of voltage. So we need to set a default boot voltage with our resistors here. And that's what they do. So for instance, in this case, I just have it set for 0.975 volts. That detail doesn't matter. I don't even really check what voltage most GPUs boot at because it doesn't matter. Somewhere a bit around there probably for a GTX 260. And then once the GPU is on, it can use these GPIO pins to control the voltage on these pins, the vid pins, to basically put these as either high or low, and it can even overpower most likely these resistors such that they don't matter, and then it can control the voltage how it wants. Now you will notice something, that typically there is not a GPIO pin for every vid pin because we don't need one. And you can save space, less pins on the GPU used, less traces that have to go all the way across the PCB. It's simpler that way. So for instance, we already know that the GPU is probably not going to care about controlling vid 6 and 7. Sorry, 5 and 6 here. In most cases, we have a pretty set narrow range that we know the GPU is going to run the voltage at. We also don't need super fine resolution, most likely. Changing it by 6.25 millivolts, really not important. The controller's not real, like, doesn't make a big difference to the controller anyways. The 12.5 millivolts is probably enough resolution anyways. So in 4 GPIO pins, we can get quite a range of voltage already, and we don't care if vid 6 and 7 are held high, doesn't matter. In practice, you might actually have vid 6 controlled by a GPIO pin, or vid vid 5. It really doesn't matter exactly. This is just an example. So then when we want to look at vid modding a controller like this, what we want to do is disconnect the GPIO pins from being able to influence the vid so that we control it. Now, if, for instance, if this was still connected because for some reason there was just a via that you couldn't really cut the trace between, it would just cause too many issues. You can try to overpower it with switches. So for instance, instead of just single pole, single throw switches, you'd use a dual pole switch that would also alternatively connect to ground. So going up to like a ground connection. And that way you try to overpower it by connecting it either directly to 3.3 volts or directly to ground and try to overpower this GPIO. That has all sorts of issues with it. I would avoid that if at all possible. There's like a risk of basically damaging bits of the GPU core. Now, are those critical bits? It's hard to say. But avoid that if you can, obviously. So in this example, I have vids 0 through 5 controlled. We're just going to connect the last two vids to ground because I didn't really show this before, but you can get enough range without those last two vids for basically all your overclocking needs. You don't need to be able to go down to 0.8 volts or below that. It just is not practical at all. And you can boot cards at higher voltages than their typical boot voltage. Is not an issue as long as your cooling is good. And again, we're talking about overclocking here, and competitive overclocking, we can provide that. It's not a big deal. So basically what we want to look at here is how I have all of these switches that connect the vid pins up to 3.3 volts. Now, the important part about that is that by default, remember, there are pull downs. So by default, these are a logic low at about 0 volts. Then when we alternatively connect it, we can then provide our own vid code to the VRM controller, and then that will control the output voltage accordingly. So from this, pretty simple, like the mod is pretty simple. It's disconnect GPIO, connect switches. Now, as you can already tell, this takes a little bit more. It's a little bit more involved than your typical feedback mod because we have to, disconnect the GPIO, which can be sometimes a pain, depending on the card. And we have to wire in multiple switches, which can suck. But this is the point where I would say on certain controllers, you can simply set up your vid such that you get either 1.2 volt vid or 1.4 volt, and then use feedback mods from there to basically, get your range in between. And you can get a pretty good range that way where you have one switch, one feedback mod, and it's not too bad to do. And this is how you get around a lot of the issues on like over voltage protection. You can do that as well in there. So now, getting down to the actual cards that I modded. So this card, well, the only card I modded so far, this is a BFG Max Core 55 that's already been kind of modded. This is an in-between state when I took this picture. And basically what you can see from here is I labeled where all the vid pins are. So you always want to connect on the right side of these resistors on this PCB. This is where vid 0 is, 1, 2, 3, 4, 6. You'll notice I skipped 5 and 7. That is because vid 5 is connected to absolutely nothing. It is a single pin here that is disconnected from everything, and such is a giant pain to solder to. We will talk about that a bit later when I show my actual example. You can solder to it, is just a pain. And not having vid 5 means you're basically limited to vids 1.2 volts and below and 1.4 volts up as your only real easily achievable vids. So you'd have to use a feedback mod to get 1.3 anything. So in that case, you'd set your vid to 1.2, use that up to about, you get 1.2, 1.3 with your feedback mod, and you have to go higher, you have to change your vid all the way up to 1.4, and then you use your feedback mod from there. And you could technically set it to 1.4 and go down, because you get a bit more range going down from your under voltage protection. But then you're also going to have a lot of droop. So ideally, you might, you set up your feedback mod such that you do that, but then that would mess with your compensation loop. It just gets complicated. So ideally, if you can solder to this, it is difficult, but doable. Also, you'll notice here, this is where your GPIO pin connections are. So basically, vid 3 goes into this via, vid 2 goes into that via, vid 1 goes into this via. Don't worry about this via, that's something else. And then vid 4 kind of continues along here and goes into this via. So to basically disconnect this, these are really easy. You just desolder your resistors. These resistors connect these are all ground, so the let's look at, for instance, vid 0. Vid 0 just kind of comes through here and sorry, comes past and then to this resistor, through the resistor to the via. So if I want to disconnect vid 0, if I desolder this, we're all good. It's already disconnected. All of these vias here are for ground, so these resistors are all pull downs, so they're 10K pull downs. This really isn't necessary. Detail doesn't matter, just leave them alone. So for vid 2, similarly, vid 2 comes through here like this. So it has a 10K pull down, a nice pad you can solder to here as well, and then it connects through there to the via. So to mod this, all you have to do is desolder this resistor, and then you would solder your switch here onto that one, the middle pin of your switch. And then your other side of your switch will go to 3.3 volts, which is either here. This is the 3.3 volts produced by the controller. There's also 3.3 volts there. Doesn't matter which. Vid 6 here, by the way, is connected just directly. So it goes something like this, and then it just connects directly to 3.3 volts. So if you desolder this, you get no 0 volts on vid 6. Vid 4 is connected just to ground, if I remember, well, to ground and then through to this via. So to disconnect vid 4, I had to cut the trace here, and that's what that kind of big mess is. I had to cut deep into the PCB, cut the trace completely, but I managed to do that, and it's all good. So this is actually not too hard to vid mod. As you can tell, this is the only real pain. So now I'll show on the actual card what the vid mod looks like. So you can see here already that, I got this bit more frame. You can see here all the wires that I used. It's very hard to tell, but there's this small wire here. That is a tiny piece of magnet wire that is connected to vid 5. I'll put the picture up right now about what the solder on that looks like briefly. Basically, to do that, I just used a ton of flux and make sure you don't have too much solder on your iron. Carefully hold the magnet wire right near there after it's been pre-tinted and just kind of jam it into the controller pins. And with enough attempts, I managed to do it even without a microscope, so I'd say it is very doable. You just need a good way, some magnification, to be able to check later if it's soldered properly. Yeah, basically from there you can see this is actually this wire here. Here's the 3.3 volts. It connects, let's get this. There we go. Kind of hard with this. This wire goes along the top. That connects 3.3 volts to one side of all of these switches, and then the middle pin is the one that's switched either to 3.3 volts or just to the floating side. The floating side doesn't matter. These are single pole dual throw switches. If you have single pole single throw, it works the same way. The dual throw ones, you just leave one side empty. This is actually the edge of the PCB, so this entire edge on both sides here is all ground. So I just basically scratched some of that away and soldered this directly on, so it's held on even more firmly than if you hot glued it, which is kind of nice. And yeah, there's basically, yeah, you have your 3 little wires here that go to each of those resistors. So when I implemented mine this way, all I did was vids 5, 4, 3, and 2, I believe. Yeah, I think that's it. 5, 4, 3, 2. I don't need much resolution, actually, in my personal opinion. If I wanted more resolution, I'd add the potentially a trim pot in addition with it. I might still add 1 and 0, but honestly, the 4 switches are probably good enough for me most of the time. And yeah, you don't really need a ton of resolution, honestly. If you ever mess with a trim pot mod, you already know that like your effective resolution isn't that good often, and that often is good enough anyways. So I just would wire in the 4 switches like I did. If you wanted to not solder to vid 5, just solder to vid 6 instead. So do 6, 4, 3, and 2. And with that and a feedback mod, you can get more than enough control. Actually, even if you just do 6 and 4, you can already get your either 1.2 or 1.4 volt vids, and then just use a feedback mod from there. So yeah, I would actually just say like that is what everyone should do if you want your full voltage range to be able to control it. And anything beyond that is just extra. So like, yeah, basically the extra bits of here are just for a bit more resolution. And if you want to be able to get the really high voltages, so basically turning off, like getting well over 1.5 volts for sub-zero overclocking, you need the extra vids. Ideally, you want to get as high as possible, and then your trim pot just goes beyond that. to maximize the mass voltage. But you really don't need more than 1.6 volts if you're not an LN2. 1.5 something is probably where most cards would max out at anyways on something like dry ice or chilled liquids, like Sub-Zero liquid. So yeah, I think that pretty much covers it. I can do a soldering example maybe if someone really wants it, but there's really not much point in my opinion. You just see an iron sticking in there. The points are very small, and I don't have a microscope to show it really well. So yeah, I mean, there's really not much to it. If your card's very different and you're unsure, just take some good pictures and send them to me on the HGBot Discord. And I'll try to help the best I can, especially if the information's good. But yeah, a lot of it is just once you figure it out, like I showed here, like, oh, this side connects to ground of these resistors. These ones are probably GPIO pins. Once you figure that out, it's pretty straightforward to just desolder the stuff you need to, add in your own switches, and call it good. Okay, bye.